When you hear the words geothermal, do you think of drilling deep into the Earth's core to harness its energy? One main obstacle to widespread adoption is the perception that geothermal cannot be implemented in urban environments. However, our proposal overcomes this problem by deploying a geothermal district heating and cooling system in an urban environment. MIT's campus in Cambridge, Massachusetts. The MIT campus presents a major challenge for a zero-carbon district HVAC system. Space is limited, buildings are of all ages. Campus is built on type of land usually considered unsuitable for geothermal. Geo at MIT is excited to present our proposal for a new generation zero-carbon HVAC system. The plan achieves zero-carbon status by 2035, 15 years earlier than MIT's current plan of 2050. Our approach can be a key component of a brighter, more sustainable future. We are Geo at MIT, a group of MIT and Harvard students who have backgrounds from mechanical engineering to computer science to business administration. We also have a certified geothermal driller on our team. We are guided by faculty advisor Susan Murdoch, an environmental engineer and MIT D-Lab lecturer who has converted her home to geothermal. 4 advisors who have a combined 160 years experience in HVAC systems design, installation and operations, including designs for some of the advancements to be presented. Another is an expert in drilling techniques needed for urban installations. A special shout out to Susan, Rick, and Judy, and John, who have been most gracious with their time. The challenges of implementing a multifaceted GDHC system in an urban environment such as MIT's campus are location constraints. The campus is built on field and salt marsh. Energy source and distribution system. MIT currently uses natural gas for a cogeneration plant for most of its building's operations. Energy consumption. Energy usage varies widely by building, with some labs very high in usage. Cost and implementation. Implementation of the system must not cause major disruptions to campus activities. We will be addressing the first 3 challenges through our technical analysis of our proposal.
To meet the differing energy needs across campus, we are proposing a hybrid system with both centralized and decentralized components. The existing central utilities plant will change from powering all of campus to a secondary supplemental role for backup and unexpected peak energy loads. The decentralized component is an innovative integrated geothermal system that consists of 6 main components aimed at meeting MIT's diverse and challenging energy needs. Our goals with the hybrid system are to eliminate all energy losses through ventilation and exhaust hoods, provide campus-wide energy transfer and distribution between buildings, and store excess energy for use during high power cost periods. Our planned 6 key components to achieve our goals include the conversion of an existing steam and chilled water loop to an ambient heat pump loop, advanced energy recovery ventilation systems to capture vented waste heat, the installation of water source heat pumps in almost every building, the installation of thermal batteries in numerous locations throughout campus, an innovative ground heat exchanger, and additional optimizations with city water thermal connections and sewer energy recovery. The following is an example of how these components create a highly efficient 6th generation HVAC system with thermal storage in a highly high-energy lab building. It can also be scaled at different building sizes or linked to create a multi-building district HVAC system. The first step is converting the existing chilled water loop to an ambient loop with water temperature between 45 to 85 degrees Fahrenheit, enabling the energy in our system to be distributed between buildings. The loop will be connected to the other exhaust and ground heat exchanger components. Our next step is to install exhaust recovery systems in each building since there exists 50,000 cubic feet per minute lab exhaust on top of many buildings. Advanced active exhaust energy recovery units are critical to reducing energy load and achieving zero carbon. From examining EUI data on individual buildings, we know that there exists significant room for improvement in this area as exhaust systems drive most of the energy loads on campus. This building is not even the most energy-intensive building on campus, but even buildings closer to the median EUI, like Building 9, have significant exhaust problems. There's huge opportunity to be more energy efficient with the use of an active exhaust recovery system that can reduce the load, especially since the weather in Cambridge is quite mild. Inside each building, we'll also install indoor smart latest generation water source heat pumps. These heat pumps are connected to the ambient water loop and allow us to easily transfer energy between buildings as needed. For thermal storage, we'll install thermal batteries throughout campus, which are a novel technology developed by Dr. Xiaobing Liu of Oak Ridge National Labs. They utilize phase-change materials that can store and release large amounts of energy. Importantly, they've been able to find especially high energy storage densities with crystalline material. We spent time walking campus with drilling companies to find locations for such batteries, and with innovative drilling techniques, thermal batteries are feasible for urban environments. The other components of the system can be installed and operational before the batteries, making this a highly flexible system in implementation. Ground heat exchangers can be installed on campus with innovative drilling techniques that we'll take a closer look at later on. To balance out the system, we can even find additional optimizations with municipal water connections and sewer energy recovery. The bottom line here is that these 6 elements significantly lower total HVAC loads and provide the lowest cost path to decarbonization. In order to ensure our hybrid system can be implemented feasibly within the urban environment, we first examined geotechnical data of the area. In the yellow outline below is roughly the 168 acres that make up the MIT campus. The red circles indicated here show test bores that have been drilled in the Cambridge area. They show that bedrock exists below 100 feet, while the first 100 feet are fully saturated overburden. Based on drilling at the Moderna site, we estimate that we have about 732,000 bore feet available which can support 2.9 million tons of HVAC. We'll now take a look at the specific drilling techniques that will allow us to implement the system. As mentioned before, we have 100 feet of saturated overburden, and the bedrock in this area is argillite. One proposal is to use incline drilling from one area with low footprint with sensor bores as needed if MIT has any concerns. The thermal battery casings can then be installed in a vertical manner that stack on top of each other. The byproduct of this approach is that we can also do directional drilling deep beneath the buildings. These innovative drilling techniques allow us to maximize the geology of MIT's campus in a cost-effective manner while minimizing the disruption to campus activities. With this proposed hybrid system, we address the 3 main challenges with MIT's current energy needs on the path of decarbonization, which are energy loss, energy mobility, and energy storage. An added benefit with this system is that it is highly resilient with many built-in redundancies that will keep the campus running efficiently.
Next, we'll address the last 2 challenges in the stakeholder analysis. Our proposed 6th-generation hybrid geothermal system will cost MIT an estimated direct project cost of $168 million. This is possible because we will utilize MIT's existing piping network, and piping is usually one of the largest expenses. As a clean energy project, we likely qualify for IRA funding. The target break-even for the project is 5 years. Then there will be a return on investment. This compares favorably with an earlier MIT estimate of $750 million for a geothermal system. We engaged with various stakeholders, including MIT leaders, experts, and community members, to determine how our project could be implemented. MIT administration and staff, especially those in the Office of the Vice President of Campus Services and Stewardship, helped us understand decision-making, infrastructure, and operation of facilities at MIT. We learned that MIT is currently in the process of creating a decarbonization plan between now and 2050. They care about 4 main things when choosing which technology to adopt. 1, it's feasible for the space and geology we have on campus. 2, there are minimal disruptions to campus activities, especially research labs. 3, it is objectively the best solution. It is cost-effective such that it has a low carbon footprint and high energy output. And 4, it can be operated by MIT staff. From the technical experts we interviewed, we have learned more about the key components that make up our system, including exhaust recovery, ground heat exchange, water source heat pumps, thermal batteries, and drilling techniques. While presenting a poster of our GDHC plus TS plan at MIT's Energy Night and having various conversations with MIT community members, we found that many people are not familiar with heat pump benefits, nor of MIT's decarbonization plans. Currently, MACA is the only advocacy group working on the decarbonization of MIT's buildings. However, the MIT community overwhelmingly supports a shift to green energy. This parallels the many policies being passed by local, state, national, and global governments as we work towards a sustainable future. All these stakeholders were intrigued with our GDHC plus TS system and were very supportive in our exploration. We hope to help bridge the gap between MIT leaders, experts, and the public so that we can all work together to decarbonize MIT. This work would not have been possible without the support of all the people acknowledged here. We plan to continue working with MIT, MACA, and other stakeholders to explore the role geothermal technologies can play in decarbonizing our campus as efficiently, quickly, and cost-effectively as possible. We believe this project can become a reality and hope to host public town hall events in 2024 to share our work widely and receive feedback. In the meantime, learn more and get involved with the links shown. We look forward to working with you all.